space vehicle is launched on a lunar mission, the return trajectory must be so shaped that the vehicle will re-enter the Earth's atmosphere at or near a prescribed latitude and longitude. The flight conditions at re-entry must be such that the vehicle may re-enter safely and be able to maneuver in flight to attain the desired landing site. This means that the flight path angle, that is the angle between the vehicle direction of motion and the local horizontal at re-entry, must be within prescribed limits depending on the aerodynamic characteristics and mass of the vehicle and on the density of the Earth's atmosphere. For similar reasons, the heading angle must also be within prescribed limits. The Apollo is a fixed trim vehicle using a center of gravity offset to obtain a fixed trim angle, which provides a fixed lift direction with respect to the vehicle. A stabilization reaction control system has been devised, which provides rate command in roll about the relative total velocity vector by coupling both body roll and yaw jets. A re-entry guidance system was also devised, which is capable of guiding the vehicle from the point of re-entry to the prime or alternate landing sites. Errors in the return trajectory may cause the time of arrival at the Earth's atmosphere to differ by as much as several hours, and re-entry will then occur possibly several thousand miles of Earth longitude from the nominal point of re-entry due to the Earth's rotation. Errors in the trajectory plane inclination may also cause the latitude and heading angle at re-entry to be in error. Mid-course guidance is assumed to correct the vacuum perigee altitude before re-entry occurs so that the flight path angle at re-entry falls within tolerable limits. Similarly, mid-course guidance is assumed to correct trajectory plane errors so that the heading angle at re-entry falls within tolerable limits. Corresponding to any stage during re-entry, a typical footprint of landing points could be drawn connecting all the landing points achieved with trimmed lift and modulated lift vector angle. Within this locus lies the zero lift impact point achieved on Apollo by rolling the vehicle at a steady rate above a minimum value. For the target to be accessible, it must always lie within the current footprint boundaries. For an equatorial re-entry, cross-range capability may be used to cancel errors in re-entry latitude, while down-range capability may be used to cancel out errors in re-entry longitude. For this simulation, a target has been selected to demonstrate that a particular re-entry guidance technique may be used to guide an Apollo vehicle along a safe trajectory to the selected landing site. By safe is implied that the vehicle shall not be subjected to excessive deceleration or heating and shall not skip above a prescribed altitude. The limits used here are 10 G and 500,000 feet in altitude. The guidance scheme simulated uses a prediction technique, continually predicting the zero lift landing point starting from present flight conditions. The prediction is updated every few seconds and is displayed on a cathode ray tube in the simulator cockpit. For convenience of mechanization, the current zero lift landing point is the scope center, with the selected target as a moving dot. Scale selectors provide range scales of 5,000, 1,000, and 120 nautical miles. Below the cathode ray tube is a display of the direction of the lift vector relative to the local vertical. The pilot controls the lift vector direction so that the zero lift landing point is driven towards the target. Command is effected through a displacement type hand controller. Body angular rate damping is provided about the commanded rate in roll and yaw and about zero rate in pitch. A red warning light comes on when the zero lift predicted trajectory exceeds 280,000 feet. And a yellow-green light comes on when the zero lift trajectory exceeds 10 G. When either light comes on, the pilot takes action to restore the zero lift trajectory to lie within a safe region. Two Electronics Associates 231R analog computers and associated readout equipment were used for the simulation. Vehicle motion was programmed in 6 degrees of freedom about a spherical rotating Earth, including 1959 ARDC standard atmosphere.
The predictor equations programmed were point mass in 2 degrees of freedom about a non-rotating cylindrical Earth model and using 1959 ARDC standard atmosphere. The predictor equations programmed were point mass in 2 degrees of freedom about a non-rotating cylindrical Earth model and using 1959 ARDC standard atmosphere.
On one XY plotter is traced dynamic pressure against time, while on the other XY plotter is traced altitude against downrange distance. The large XY plotter traces out the coordinates of the target in an axis system which moves with the vehicle. Displacements in the vertical direction are proportional to the cross-range distance of the vehicle relative to the target. Displacements along the horizontal scale represent distances of the vehicle relative to the target along the direction in which the vehicle is heading. The remaining outputs of interest are recorded on 2 8-channel recorders. These record flight variables which will be analyzed at the conclusion of the simulations. To obtain results as early as possible, a simple pilot's display panel was used. The main instrument is the predictor. Below the predictor is the lift vector direction indicator. The Q-bar indicator gives the dynamic pressure. To the left are the altitude and velocity indicators, the flight path angle indicator, and the rate of change of altitude indicator. Let's watch a typical simulated re-entry. Our initial flight path angle is minus 6 degrees. Our re-entry altitude is 400,000 feet, and our velocity is 36,000 feet per second along an equatorial trajectory. The target is located 3,000 nautical miles downrange of the re-entry point and 300 nautical miles cross-range. On passing through the 400,000 foot level, the pilot ensures that the vehicle is oriented with the lift vector pointing down, inclined slightly in the direction of the lateral range error. Slowly, the dynamic pressure builds up, and the lift force starts to oppose centrifugal force. During this time, the predictor display is inoperative, and a red light indicates that we are above the skip altitude. As we enter the sensible atmosphere, a flashing red light indicates that our zero lift trajectory would skip. We continue to maintain downward lift. Finally, the predictor target dot appears and is allowed to move ahead of the scope center, or zero lift landing point. The vehicle lift vector is reoriented so that it is in the same quadrant as the target dot, pointing in the general direction of the target, such as to reduce both longitudinal and lateral range. The zero-lift landing point is now very sensitive to lift vector orientation, and the astronaut is careful to keep the target a few hundred miles ahead of the zero-lift landing point. Positive longitudinal range is easier to obtain than negative, and in addition, an approximation in the predictor, due to the use of a non-rotating Earth model, causes the zero-lift impact point to move slowly ahead as velocity decreases from supraorbital to orbital values. As the dynamic pressure decreases, lift becomes less effective, and the vehicle follows a ballistic trajectory. Altitude is increased up to a peak or skip level, at which point it decreases again. Note that the target is slowly moving toward the scope center, even though we are outside the sensible atmosphere. With a second re-entry into the sensible atmosphere, the dynamic pressure builds up again. The pilot again orients the lift vector to cancel residual lateral and longitudinal range error. Lateral range error must be cancelled while the velocity is high, and is much harder to reduce than longitudinal error. When nearly all the longitudinal error is cancelled, the bank angle is set near 90 degrees or 270 degrees, and residual lateral range error is eliminated. Upon closing the range errors to within prescribed limits, the pilot may elect to either continue orienting the lift vector alternately on either side between 90 degrees and 270 degrees to keep the target near the scope center, or to go into a steady rate of roll for the remainder of the flight. The XY plotter shows that the vehicle is heading directly on target. Dynamic pressure is falling, and altitude is nearly 100,000 feet, the altitude at which the flight is stopped. Below this altitude, little range can be gained because the velocity of the vehicle has been substantially reduced. The simulation you have seen is typical of the intensified research being carried on in the Apollo program. A program not only to place a man on the moon, but also to bring him safely back to Earth.